So our next presentation is from Dr. Martin Entz. It's titled Designing Resource-Efficient Resilient Cropping Systems. Professor Entz has always enjoyed the outdoors and working on the land. He's received his bachelor's and master's from the University of Manitoba and his PhD in crop physiology from the University of Saskatchewan. He worked as a farm manager at industry research agronomist before embarking on his academic career. So, Martin, I see you didn't wear your Hawaiian shirt today. You didn't get the memo, I guess, so.
No, I must have had too much cadmium. Okay, good morning, everyone. Thank you, Tom. It's good to see you. So, I'm talking about this subject, and while they're getting a full screen here, what I did is I broke up the, thank you. I broke up the inputs into what I call store-bought inputs and free inputs, because I'm just going to test out my mouse. Does this work? Is this the mouse? Does this give me the little red thing that Tom had? Okay, got to bring it over. Okay, there we go. Okay, all right. To be educated, it's a wonderful thing. So I broke up my inputs into what I call store-bought inputs and free inputs. So store-bought inputs are things like fertility and in chemicals, and they're very much based on fossil fuels. And the free inputs are things like photosynthesis, the atmosphere. And I also put people in there. And because people are, well, they're not free, but they're really important. You're agronomist, you're part of many farmilies. I heard this term at a conference that many farms actually work with a community of people, and I love the term farmily. Free inputs are very much based on solar energy. So those are a couple of distinctions that I'd like to start with. Okay, page down. Let's go. There we go. Okay, now when we think about our store-bought inputs, the number one expense is fertility, and the biggest one there is nitrogen fertilizer, accounting for about 30% of variable costs in Manitoba. So this, for me, raises a lot of questions, and so when we talk about resource-efficient rotations, we want to think about what makes nitrogen use efficient. We want to think about ways of improving nitrogen use efficiency, for example, using no-till. And if it works, why does it work? What about these soil additives and biologicals that are out there now? And how much nitrogen do we get from late-season cover crops? So I'm going to start my presentation by focusing on some of these questions. This here is data on canola from many prairie locations, and it gives us sort of the agronomy 101 of nitrogen use efficiency. We see an increase in canola yield with added nitrogen, no big surprise. At about 50 kgs in this case, the slope of the line declines, and over on the right, we see a steady decline in nitrogen use efficiency. So, we want to be operating here where the level of efficiency is very high. And we're going to hear later today about nitrification inhibitors and all these coatings. I think Regis is going to give that talk. But we do know that the 4 Rs are quite effective at helping boost that nitrogen use efficiency at least a little bit. And I'll leave that for others to talk about. There's other factors that influence this question. And one of them is the rising daytime temperatures in the summer. So again, research from multiple locations across the prairies, where researchers found that heat-stressed days and heat-induced thermal accumulation actually reduced the nitrogen use efficiency. And on the right, there's a very fancy heat map, which on the x-axis on the bottom shows the number of days above 29.5 degrees Celsius, and then it gives the economic optimum nitrogen fertilizer level. And you can see that as your heat days goes up, the amount of nitrogen you need to maximize yield goes down. And I thought I would highlight this because it does really speak to a crop that is at risk of doing less well as the temperatures rise in this part of the world. And maybe for agronomists, and I know this paper alluded to the possible use of split application nitrogen to maintain high nitrogen use efficiency. Do no-till soils increase nitrogen use efficiency? Well, David Franzen from North Dakota State University has done a lot of thinking about this. He writes and makes observations that no-till soils have higher microbial biomass carbon, the living carbon, that's a good thing. But then his latest study was really interesting on the right-hand side, showing that the nitrogen that is derived asymbiotically, which means outside of the plant, was actually higher on long-term no-till farms, commercial farms, than long-term conventional till farms. And so that's quite interesting, and it's kind of new, and it gives us a little bit of a mechanism. We do have a little bit of free living nitrogen fixation happening in these no-till farms, which is great. We also know that, we just heard about pulses. We knew 25 years ago from research in Saskatchewan that pulse crops actually derived a higher percentage of their nitrogen from atmospheric sources in no-till versus conventional till. So no-till has been a very positive practice for nitrogen use efficiency. What about these biological products? And many of you will have heard about this work, which again was led by Dave Franzen with many really good scientists across 10 US states, where they really found no benefit of any of these products. Now, that doesn't mean that that may not happen in the future, but that's where we're at right now. Do legumes increase nitrogen use efficiency? And I really appreciated Tom's enthusiasm for getting more legumes into the system, because they do. They're very important. And if you look at the graph on the left-hand side there, as the percentage of nitrogen that comes from fixation increases up to, say, 20% to 40%, we're getting higher nitrogen use efficiency overall. So maybe that's really, as agronomists, what you can take on board. Can you design systems that provide that percentage of nitrogen from fixation? I think we can. Our research has certainly shown that through the mechanisms that I've listed on the right-hand side. Am I going too fast?
No.
All right. Am I going too slow? Okay. All right.
That's your Siri button.
That's like my kids go, Dad, got it already. Okay. So this is just a little bit of an highlight off of our Glenlee long-term study, where we look at two conventional, not organic, conventional rotations, and we look at the energy budget that is involved in wheat production in two rotations, one that's only grains, soybean, wheat, flax, oats, and one that's 2 years of alfalfa for hay, then wheat, flax. And not only are we using less fertilizer, which means we're using 25% less fossil fuels in the forage grain rotation, we're also getting a higher efficiency of that fertilizer nitrogen use. There has been a lot of enthusiasm for late season legume cover crops, and work that we did quite a while ago shows that there's a good 10 million acres of land in Manitoba, which is very, very suitable for late season legumes, even though there's been quite a bit of pushback on that because of maybe one failure in a dry fall. The value, increased nitrogen, and the second value is that growing something in the fall reduces the water-filled pore space, and if you have saturated pore space, you've got the potential to lose nitrogen in various mechanisms, including nitrous oxide. So we did this work about 20 years ago, which is shown on the left, where we relay cropped alfalfa and red clover into either winter wheat or fall rye, or we double cropped chickling vetch or lentil, which means seeding it right after the harvest of either of those winter cereals. And we found that the fertilizer that legume replaced was from 23 to 62 kgs per hectare. And this research has been out there a long time. About 10 years later, we redid the work in organic production, both no-till organic and conventional till. And there we figured out that, we didn't have the benefit of using N15 because my lab's not set up for that, and we just never really had the resources to do it. But there, every 1,000 pounds per acre of biomass of legume that we produce in the fall gave us about 7 bushels of additional wheat per acre the following year. Now, that may not be quite the case in conventional, but in organic, we tend to be nitrogen limited. So that's what we learned there. So these fall cover crops can do quite well, and I'm just going to give you a few examples. On the right here, this is your standard sort of Southern Ontario practice, which can work quite well in Manitoba, red clover relay cropped into winter wheat. On the left, we've got hairy vetch, which we seeded after winter wheat. Hairy vetch is an incredibly good nitrogen fixer in a league kind of where faba bean is. And here we've got a pea crop. And all of these systems. And one of the things that I'd really like you to giddy up on is some equipment fun with cover crops, because there's lots of ways of establishing cover crops, and let's use our imagination. The one on the right I love. You put a Gandhi applicator in the front of your combine and you spread your seeds. This is what farmers are doing. And I think there's been a reluctance in innovation here. Okay, so we're growing. I'm saying that you should think about upping the amount of legume in your system somehow, and you have to be careful of Aphanomyces and Fusarium root rot, and you need to select legumes wisely so that you're not building up these diseases, and there's many to choose from. If you put on your organic agronomist hat, which I really encourage you to think about, is then we need to think about mineralization. And managing mineralization in these legume-intensive systems. So on the left here, we've got our green legume plant growing, and the decomposition, the speed of that decomposition is something that can be managed, and it's important to know. In our work, we've worked with lots of livestock. This is the #1 way to quickly make that legume nitrogen available to crops, because the urea comes out of the back of the animal. The second most effective way is tillage, like disking. The third speedster is flail mowing. And then we start slowing down the nitrogen release, wide blade cultivator, and then finally the blade roller. And you may want to use combinations of these to manage the supply rate of that nitrogen, because it is possible. It is possible to do that. When you're in a drought, putting animals on top of those legumes will make it immediately available. One of our RBC summer students, Julia Beechner, did some work last year looking at nitrous oxides in these various green manure termination systems, and we do see evidence that the blade roller has lower nitrous oxide emissions. So I've talked a little bit about nitrogen. I've only got a short period this morning. What we did is Joanne Thiessen-Martens led the production of a budgeting tool for legumes in organic systems. It's now an app. You can download it. And I'd just like to alert you to some training sessions we have in February on the use of this app for agronomists, so please sign up. Okay, so let's turn to our free resources, ones that are really based on solar energy. I wrote a recent book chapter on agriculture as a mimic of natural ecosystems. I can send you a copy if you'd like. But I love this carbon cycle from Wikipedia, which describes the flows within these natural ecosystems. You get the solar energy coming in, you get photosynthesis, those are green blobs are coming into the system. Some of that is respired back up. You've got the water cycle. There's 7 rules that I've written about, and this is really inspired by Ted Lefroy from Australia and Wes Jackson and the Land Institute, Kansas. But energy flow is self-regulating. Can we mimic that in agricultural systems? Well, I think we need to in Manitoba, because if we look at the change in soil carbon over 35 years, we're not doing very well. Really, organic matter in soil has not changed much over 35 years in Manitoba, nor has it in northwestern Alberta. And that's because these areas use a lot of tillage. They don't use a lot of cover crops. Perennials are no longer a big part of the rotation. Saskatchewan has built up their carbon, but that's because they eliminated summer fallow through water conserving no-till. So there was nowhere for them to go but up. But anyways, if we look at Manitoba, how can we think about the natural cycle of carbon and add some carbon to these systems? The only way is to increase photosynthesis. And there's lots of energy to do that. We have the solar resources. And so I want to spend a little bit of time on this data slide which depicts the results of Samantha Curtis's master's project, where she looked at over one growing season, it happened to be a fairly dry year, where she looked at the above ground biomass in different crops every 3 weeks through the growing season. So let me begin at the left. In early April, late April, we have a little bit of growth. This comes from a longer term study that we had at Carmen. Perennial wheat or Kernza intermediate wheatgrass is starting to produce some new growth. So is hybrid fall rye. It's giving us some growth. So by the middle of May, we've already got 1,000 kilograms per hectare of fall rye. When would we want to seed soybeans? Maybe here. We might already have 2,500 kilograms per hectare of fall rye. Keep that in mind. I'm going to give you a farm example later. Our spring seeded cool season crops, wheat, canola, you can see they do really very little photosynthesizing until well into June, even though we might seed them on the 5th of May. They're just so small. And by the end of August, they're pretty well done. So if a canola wheat is our predominant farming system, we're really not capturing as much of that photosynthetic energy as we could. We look at corn, sunflower, well, they do what they do, right? They're awesome. And then if we look at soybean, it extends that a little bit longer, which is good. And then these fall, these little bits of dry matter in the fall are from either cover crops that we had or Kernza or the fall rye, which was planted in the fall. And we're getting less than, about 1,000 kgs, which is not nothing, which is 7 bushels of wheat. And then we have this corn-soybean intercrop here, which is quite interesting. This one actually never received any nitrogen fertilizer ever in the 4 years of this study, and it's now become my favorite intercrop, better than pea canola, and that's a pretty good intercrop to begin with. So I'll just leave you with that. The second part of the flow of systems is water. And water is harder, I think it's harder to deal with than carbon, because look at the wet and dry cycles in the Red River Valley from 1800 to 1983. Is there a pattern? The dark blobs are wet, the hashed are dry, and the clear are average, and there's no rhyme or reason. And anybody being an agronomist in the temperate regions of the prairies knows this. But we do have to think about balancing the hydrological cycle, because otherwise we're dealing with salinity problems in those wet years, and we're dealing with, if we grow soybeans, we're dealing with salinity problems in the dry years. And so on the left, I've just got an alfalfa root growing at the Glenley Research Station, and you can see the salt stays in the soil when you grow a perennial that uses that water. So. And here's just some recent data from Iowa looking at corn in a 4-year rotation versus a 2-year rotation, and corn in a 4-year rotation roots deeper. And so there's values of diversity. Just checking the time here. Okay, now a little bit of theory. When we're optimizing in order to optimize these free resources, we need a system redesign. So Stephen Gleesman and many others have written on the steps to sustainable agriculture. Step one, we increase the efficiency of conventional inputs. We talk about that all the time. Step two, we substitute conventional inputs with alternative practice. So instead of using a herbicide, you might use one of the fancy machines that Matthew showed us yesterday. But what's really important is that we redesign systems that function on ecological principles. And here's just a little bit of the way to get there. So energy flow in natural systems is self-regulating, so mimic this. So if you're an agronomist in an area, take a look at what's natural in that area and mimic that as much as possible. Secondly, promote mutualistic functions. Tom talked about biological nitrogen fixation, really important. There's other ones. Predator-pest relations. Yesterday, Matthew talked about their strip cropping of soybean, wheat, and maize, and the reason they did that is to control aphids in their organic soybeans. Putting a lot of fossil fuel energy in our cropping systems makes them monoculture, reduces mutualistic function. Increasing biodiversity increases mutualistic function. I'm going to give you an example. Tom covered biological nitrogen fixation nicely. This deals with mycorrhiza, beneficial or other fungi in the soil. On the left, we have flax. On the right, we have sorghum. This is an experiment that was published 14 years ago. In the middle, we have the two of them growing together. When we grew sorghum next to the flax increased in size by 46%. That's pretty good. And it only cost the sorghum plant 7% of biomass. Why is that? Because the sorghum shared its solar energy through the common mycorrhizal network to the flax. That's how it works. Interesting. You get it? Make sense? Okay. So this gets us thinking about mycorrhiza. What are the farm management things that result in good mycorrhizal colonization? And this is from the 31st and 32nd year of our Glenlee long-term rotation, and we definitely see more mycorrhiza in the organic system. And we probably want to be in this sweet spot here because we do want to add some phosphorus with the manure. And this is probably one of the reasons why organic sometimes punches above its weight in terms of weed competitiveness and in terms of yield potential, because there is something about the biology that's different. Okay, I want to end my talk with two examples, one from research and one a real farm example. This comes from Sam's master's project that I referred to earlier. We had compared 4 different cropping systems at Carmen. This is our base rotation, wheat, canola, wheat, soybean. Then we had what we call a warm season, or some people called it a high risk, high reward rotation, canola, sunflower, corn, pinto beans. Then we had our biodiverse rotation. On the left was a corn, soybean intercrop, canola, pea intercrop, then a green manure year, fall rye, followed by a cover crop. The organic one I'm not going to talk about here. And that biodiverse rotation operated at 50% as much nitrogen fertilizer as all the other rotations. You can download the paper if you're interested and look at these graphs in a bit greater detail, but we evaluated those systems on the basis of a whole bunch of parameters such as water use efficiency, yield, economics, rotation stability, and certainly the biodiverse rotation outperformed the base rotation very nicely. The high-risk, high-reward rotation did really well until we ran into herbicide-resistant weeds in our pinto beans. But I should say that we took this intercrop to grain harvest, not silage. And right now we don't have a machine that does this commercially, but it won't be long, somebody will invent one. And I want to say one thing about crop rotation, and it's from this meta-analysis around the world. To answer the question of how many crops in rotation are enough, in terms of small grain cereals, a lot of studies show 4 crops in the rotation are ideal. But when it comes to corn, The more the merrier. That's what the data is showing. This is a crop that is very responsive to rotation. Why is that? Well, it's a highly mycorrhizal crop. It's got all kinds of sugars to feed soil microbes. You know, corn, sorghum, millet, these are quite amazing crops. And I want to finish off my talk by showing you a redesigned farm that tries to put some of these things together. We teach a course across, I have 5 minutes, so I'm going to slow down. Maybe I'll go back to some old slides. No, I'm not going to do that. And I'm sorry I'm not wearing the shirt. And I did get the memo. Okay, so we teach this course called Climate Smart Soils. It's across 6 different universities across the country. And one of the farm case studies we look at is 3-Gen Organics. This is a conventional pig farm with grains to feed the pigs, and Grandpa Carl, who's in the middle, decided to actually invest money when this person was in their 70s to make it organic and allow the future generation hope and good economic health. You can visit the website if you want. So a few features about this organic pork grain farm is about 1,000 acres. They rebuilt their barns so that the pigs have to have outdoor access. They use high moisture corn. They don't dry it. They put it in a silo. They use some alfalfa for their pigs. And so I want to just talk about that for a minute. 40% of the diet in gestating sows is alfalfa. Pigs like us are omnivores. I had a salad for supper last night after I got frostbite cross-country skiing, and that was my reward, salad. Locally produced salad in the winter, by the way. And so that change in the pig's diet allowed a deep-rooted crop to be put in the rotation. This is their wheat. And then they were really interested in this idea that has really been promoted by like the Rodale Center, where you grow fall rye, you crimp roll it, and then you zero-till your soybeans into it. How many of you have heard that, seen that? Okay, a lot of you, almost nobody. And so, you know, they tried that for 2 years, and I was on the farm when they did that. It was okay, but they actually decided to cut the fall rye, sell it as bales, then go through with a high-speed cultivator and plant their soybeans and get a very good organic soybean yield. So remember that solar capture graph that I showed you. There is biomass available by the 20th of May to do this kind of thing. So this is the farm that Grandpa Carl reinvested in, rebuilt the barns to organic standards. And they have both solid and liquid manure. And I want to talk a little bit about this. They test their manure, which any good agronomist would promote. The solid manure is in a variable rate spreader, like we heard about yesterday. The liquid manure, high in nitrogen, used to top dress the corn. And then they, I had never seen this before, but they're very aware of compaction, and so they've got this tire pressure control system, which allows them to reduce their tire pressure very low when they go on the field and pump it up when they drive on their roads. They use cover crops, and they've also recently introduced some other crop livestock integration. So I thought I would end with that sort of real farm story, and I'll end there, and I'd like to acknowledge my team. And thank you on behalf of the Natural Systems Agriculture Research Group, which is the group I lead. These are the people, this is where we work. And I also want to say that all the publications that we produce, 95% of them are open access, and you can download them from our website. So thank you very much.
For a couple questions. Do we have any questions from the audience? I think Anna's going around. Anna has somebody up there.
Is it on? There you go. Hi, I was just wondering, for your corn and soybeans intercrop, were you using like a forage soybean or like a long season and focusing on the corn?
No, we were using, I forget the variety, it's in the paper, just a standard soybean, Roundup Ready soybean variety, not forage. And I mean, we did not have, we harvested it by hand. Yeah.
Okay, thanks.
Is there anything online, Marla?
Yeah, let's, hold on. It's a hairy vetch question. In your estimation, how well would hairy vetch establish in a very, capitalized very, sandy soil that is in pasture currently, thinking we could broadcast the seeds and intensively graze the paddock to seed the veg in? And next, what is your thoughts on cattle preference to graze veg?
Hairy vetch was first tested at the Brandon Experimental Farm in 1905, and they described it as something that the livestock really didn't love, and we noticed that with our sheep as well. If I were to graze broadcast a legume into a pasture, I would use Sicer milk vetch, which self-seeds better than hairy vetch, and I wouldn't broadcast it, I would drill it in.
Well, thanks again, Martin, for just another quick round of applause for Martin here.